To answer your question, we are now.
And then what is an example of a real, like a practical example of a capacitor that we use every day?
Every day?
Would my cell phone be considered a capacitor? Or it has a capacitor in it?
Well, it has a lot of them in it, that's for sure. Um, I don't know that there's any electrical device that doesn't have one or more capacitors in it.
AED. The
AED?
defibrillator,
Perfect.
electric defibrillator.
Thank you.
Yeah.
Okay, so what type of electrical component consists of conductive surfaces separated by an insulator?
Bravo.
Now, those conductive surfaces don't have to be flat plates or foils. It could actually be the surface on, say you got two wires that are close together. You're going to have capacitance between the surface of those two wires. So unfortunately, there's capacitance all around us. I mean, anytime you have conductors of any shape or size, you will have some amount of capacitance between that and another conductor. And there'll be some electrostatic field. What electrical component stores energy in an electric field?
Bravo.
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 What describes the ability to store energy in an electric field?
Delta.
Delta.
All right.
Delta.
What is the unit of capacitance?
Alpha.
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 All right. Named after Michael Faraday. Okay, inductors. We make an inductor from a coil of wire or conductor. And when current flows through that conductor, it forms or creates a magnetic field around the conductor. You can use what's called the right-hand rule. If you point your thumb in the direction of the current flow, excuse me, conventional current flow, then your fingers wrap around will show you the direction of the magnetic field around that conductor or wire. So it's a circular field around it. And in that magnetic field, like the capacitor, we store energy depending on how strong the magnetic field is. And that ability, just like in capacitance, is the ability to store energy in an electric field. Inductance is the ability to store energy in a magnetic field. And we use the unit of Henry, which is another one of those old guys, and we use his name, and we use a capital H to represent Henrys as units of inductance. This shows a typical, what we call a solenoid coil, because it tends to be a linear. And as current flows through it, you get that magnetic field around the wire. And because it's coiled up, the magnetic fields concentrate in the center. So you have a higher concentration of magnetic flux in the middle of that coil than you do on the outside. And that's where most of the energy is stored. To do the water flow, it's kind of equivalent to a little, say, turbine connected to a flywheel. So when you first apply water pressure, because of the inertia of that flywheel, it's going to start to turn very slowly. And as the current flows, it will go faster and faster and faster. And we're storing energy in that flywheel. It's kind of the same principle in the magnetic field. It's going to have a very high opposition to current flow when you first apply a voltage to it. And over time, okay, it will allow more and more current to flow and build up a higher and higher magnetic field and store magnetic energy. When you stop applying pressure or voltage, it's going to spin down and dissipate that energy that's stored in the flywheel or in the magnetic field. Same way a capacitor does it, except this opposes current flow initially, where the capacitor looks like a short circuit initially and opposes current flow when it's charged up. Current stops flowing into the capacitor once it gets up to its potential, which is equal to the voltage that you applied to it. And we call it self-inductance when it's a coil like that. And there's a formula for it, which again has got the permeability factor and the number of turns and the area of the coil. And the D in this case is the length of it. So those are the parameters that determine how much inductance that coil would have. This is just one showing what Faraday's law actually is, which starts to get into a little bit of calculus and differential equations, and you don't need to know that at this point. This is a typical coil. In this case, it's wound around what we call a toroid. And these are usually made out of some ferromagnetic material. It could be powdered iron or what we call ferrite, which is a mixture of some different rare earth ferromagnetic materials. And that increases the permeability, which allows it to store more energy per turn of wire on that coil. I did another circuit with a resistor in series with the inductor, and we applied a voltage, this little square wave. And as you see, the plotting voltage versus should be current, that the opposition voltage is extremely high. And as you charge up the magnetic field, then the voltage decreases down to zero. So it looks like it's just a short circuit or a straight wire after, again, 5 time constants. When you take the voltage away, the magnetic field collapses. It tries to sustain itself and creates an opposing voltage. That's part of Lenz's law, which should we do Lenz's law demo now? Because the only other places that transformer, it probably applies here more. Lenz's law says that when you apply a current through an inductor, it creates a magnetic field that opposes, or excuse me, just the opposite. When a magnetic field moves across a conductor, it creates a current. which creates a magnetic field opposing the magnetic field causing the current. So when we apply a current to the wire, it creates a magnetic field. If we have a magnetic field externally generated across the conductor, it generates current, just the opposite. But that current will create its own magnetic field that tries to oppose the external magnetic field. So we'll get Dan here. Let's see. All right. Maybe it's fall. Actually, I guess we won't. I don't have my mag. But it's an interesting demonstration. It has nothing to do with your exam, but it kind of shows you the principle of how some of the magnetic stuff works. And what we do is we've got a piece of PVC pipe and a piece of copper pipe. They're both non-magnetic. And I have a super magnet. If we drop the magnet through the piece of PVC, it takes a fraction of a second for it to travel through that 2-foot piece of pipe. If we drop it through the 2-foot piece of copper pipe, what would you say? It takes what, 5-6 seconds? About that. And it's because as it goes through, that copper pipe looks like a one-turn coil that's shorted together. So that magnetic field is creating current in the copper pipe, which is creating an opposing magnetic field, which is what slows it down. So it would almost, well, it couldn't stay there indefinitely, but depending on the strength of the magnetic field of the magnet and the amount of resistance in that copper pipe would determine how fast it or how slowly it goes through the pipe. So most people that haven't seen it get quite amazed that it takes that many seconds for that thing to drop. So what electrical component is typically constructed as a coil of wire?
Delta.
Delta. What type of electrical component stores energy in a magnetic field?
Charlie.
Charlie. What describes the ability to store energy in a magnetic field?
D.
Delta.
Delta.
All right. What is the unit of inductance?
Alpha. Oh, Henry. Oh, Charlie.
Henrys. Okay, another component we frequently see are batteries. Your kind of standard flashlight battery is what we call carbon zinc. It has a carbon electrode in the center and a case made out of zinc and some electrolyte in between that actually is what causes the through that chemical process the charges to go where the center carbon element becomes positively charged and the zinc outer side becomes negatively charged.
It's also the part that leaks out and corrodes contacts of your remote control that you haven't used in 3 years.
Yes. Yeah. It's acidic inside.
Especially here in Salty.
And these are not rechargeable. This chemical process creates that potential difference, but it's a one-way process. So once the chemical process has completed, I guess you'd say, it's no longer going to produce any voltage or potential difference. On the other side, we have a kind of an example of what's inside of a lithium ion battery, which would be one of the rechargeable batteries. And it's kind of complicated, but it does consist of an anode and a cathode, like the carbon zinc. So the anode is going to have a positive charge, and the cathode, no. Is that right?
Other way around. It looks a little backwards.
Huh?
It looks a little backwards.
Yeah, from what I thought, but it's not my chart, so. Anyway, one side is positive and one side is negative, and there's another chemical process going on with this electrolyte. But in this case, it's a reversible process. So if you apply current or a voltage in the opposite direction, you'll charge it up. So in essence, it kind of acts like an electrolytic capacitor where you can charge and discharge it. And this little chart showing typical rechargeable batteries, and the older ones, like your car battery, is what we call lead acid. It's lead plates and the sulfuric acid as the electrolyte. Nickel cadmium, which came about quite a while ago. You don't see much nickel cadmium today. One of the reasons why nickel cadmium had a what would they call a memory, and for people that keep them on the charger all the time, they would lose their ability to fully charge. So you really needed to manage them and discharge them all the way down and then charge them back up, or they would lose their part of their ability to store energy. Then
I
came
remember
lithium.
that.
Excuse me?
I said, I remember that from the
Oh, yeah.
first phones we had.
Then we came with lithium ion, which you see a lot of today. And there's various lithium types now, and you got lithium polymers, which typically you see used in like radio control model aircraft because of the amount of energy per weight. They're very lightweight. They also have, because it's in a plastic package and it has lithium in it, if that gets punctured, lithium and moisture don't go together, creates a fire. Kind of like a thermite reaction. There's been cases where somebody threw one in the back of when their plane crashed, and they were all upset and they tossed it in the back of their Jeep and went home. And the battery was, I guess, opened up, whatever, caught on fire, and it was, hot enough to melt its way through the floor of the vehicle. They've caused a lot of home fires. So that's why you kind of see them in model airplanes, things like that. It's not something you would have in your cell phone or something. Those are more like lithium ion batteries, which are much safer. They're in a hardened case.
Is something like our rechargeable Ryobi batteries for like our lawnmowers and stuff, is that a lithium ion?
It could be any of those, actually. It depends on the age.
What color is the battery?
Black. It's the ones that you just plug into the charger,
Yeah,
the big ones that,
That one I'm not sure of. That one might be a lithium ion, but the newer ones are green and I'm pretty sure they're,
Lithium iron phosphate.
yeah.
would it state it on the battery? So like if we went to go pull it out and would it have it written on it?
Say somewhere on it what it is, because that's particular to the way you charge it and which charging device you use. Because they're not all compatible.
Oh, got it.
It's somewhere on it, but it might be in scientific notation.
Okay, thank you.
You're welcome.
And sometimes you can tell from what the voltage specification is. A lead acid battery is around 1.5 volts per cell. The nickel cadmiums are 1.25,
I think it's
Different.
1.2.
something like that. Lithium ion, and most of the lithiums are like 3.7 volts per cell. So that's why you see when you put multiple cells together, different voltages. The lithium iron phosphate is a little less, 3.3 or something like that.
Yeah.
In the rechargeables, or excuse me, the non-rechargeables is your standard flashlight battery, the carbon zinc, or the ones that you have in your watch, hearing aids, the alkalins and mercury batteries. None of those are rechargeable because it's just a chemical process creating the potential difference. Which of the following battery chemistries is not rechargeable?
Baker.
Very good.
Charlie?
Bravo.
Oh, bravo.
Your car battery charges every time you start it.
Oh, right. Sorry.
Which of the following battery chemistries is rechargeable?
With, D,
Bravo.
Delta.
Delta.
The. Oh, no, the. So, yeah.
Okay, so we learned that resistors oppose
Yeah.
current flow to all forms of current. Potentiometers is just an adjustable resistor, typically used as a volume or a voltage control. Capacitors store energy in an electric field, and they're conductive surfaces separated by a dielectric. In other words, it doesn't have to be a flat plate. Inductors store energy in a magnetic field, and it's composed of coils, one or more coils or turns of wire. And batteries store energy in the electrolyte. And we have both rechargeable and non-rechargeable types.